So a numeral is when I write things down on paper. So I have this idea, like I look at my hand and I see 5 fingers and I write down that right there, right? So that right there is a symbol, it's a numeral. So on its own, there's a couple of ways to consider that right there. First, it's just some symbol, like A is a symbol and B and the @ sign. This symbol has a very special meaning. It's not a letter in the alphabet, right? It's a digit. So it's a special symbol, it's a digit. And that digit represents the idea of a number or numeral. A numeral can have multiple digits, right? So for example, 2021, that right there is a numeral. So that's another example of a numeral. 5 is a numeral. 5 is also a digit. A digit are the single symbols that make a numeral. So in our number system, we have 10 different digits. Right, the set of digits we have to work with are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are our 10 digits. And from those, we build numbers. So when I write down a numeral like this, 2021, that's not just a 2, right? That's really a 2000. And that's not just a 0, that means I have 0 100s. So I'm going to just write 0 times 100 to fill that space. And that's not just a 2, it's really 2 10s or 20. And that 1 is just a 1, nothing special there. And when kids start first learning about numbers, this isn't at all obvious. They have to be trained to realize that numbers in that 4th position over here, that those are thousands right there. And so we have this special position. And we have to learn what the next position after that is and the next position after that and so on. And so part of that learning is this expanded form I've got written out here. And this is kind of a messy one. A little cleaner would be to say I have 2 1000s and I have 0 100s and I have 2 10s and I have 1 1. And then sometimes we'll use exponents instead of writing out all of the zeros. So I could also say expanded form with exponents. That would be 2 times 10 to the 3rd and 0 times 10 to the 2nd and 2 times 10 to the 1st and 1, oops, got ahead of myself, times 10 to the 0. So this is just regular expanded form there. This is expanded form with exponents. Just a few variations on expanding. But the bottom line is what we want to do is we want to explicitly name what each digit means. And then we can use, often in the classroom, we're going to have these toys for kids to play with. Let's see, Math Learning Center has a nice set that I've linked out in our activities. There we go here. Apps. Okay, I want the number pieces. Now, when we play with the apps, I prefer the colored version as opposed to the single color, but we can change colors. So this piece right here represents my ones, and this piece right here is 10 ones or 10, and this piece right here is 10 10s or 100 ones or 100. So we can use these physical toys to talk about place value with kids and the idea of regrouping. You know, for example, if I, and let me zoom in a little bit or zoom out. If I collect a whole bunch of these green pieces, oops, putting them in bizarre places, probably doesn't like the rest of my positioning. Let's get 5 of them here. Collect those. Got them. Duplicate. So one thing we want kids to get used to, and this is a money thing too, is once you get enough pieces, you can trade it in for the next size up. So once I get 10 10s, then I can select them. And then I can join them for a new piece. And so 10 10s is 1 100. Right? So this is a physical version of the idea of our place value and our grouping with our number system. And that's related to the expanded form here. So for example, with young kids, if I wanted to demonstrate what 234 means, then I can show that with my number blocks. Let's reload. So I can get my 200s, put those here, and my 3 10s. When they're kind of like other toys we played with. When they get close, they try to magnetize together. And then I had 1, 2, 3, 4 ones. So this is a toy, a picture representation, something physical kids can try and wrap their mind around. So let's add that as a screenshot here. So there's my 234. Right, so I'm showing the expanded version. So a couple of ways we can look at that. We can say this is 234. We can use expanded by naming the place value that literally I have 2 hundreds and I have 3 10s and the idea of having 4 ones. And this is typically what we mean by expanded form here. And like when we make change with real money, sometimes it's nice to look at this number in a different way. So for example, I could break it up, say take this 100 right here and split it into 10s. So this is another way of viewing the same number. It's still the same amount of stuff, it just looks different. So let me throw that in my whiteboard. So in this version of it here, let's put it down a little lower, I'm writing the same amount, 234, but I'm thinking of it as 100. And then I have 10, 11, 12, 13 10s, and I have 4 ones. So when I write down the numeral version with its digits, there's one best way to write it. But as far as expanded, there's multiple ways to write it. And you might ask, well, why on earth would I do that? Well, if you think about subtraction, when we have to borrow a place, we might often take a number that we have to do a subtraction on, say. And then let's make it easier, make a 3 there. The 4 minus 3 isn't a problem, but when we get to the 10s, we don't have enough 10s to subtract, so we're going to borrow 100 and we're going to call that 13 10s, right? So getting kids used to that idea of different way of representing numbers by trading pieces to different place values is important, and the toys help us play with that. Put this in the chat and in the YouTube video. It's located in other places too. All right, so there it is in the chat, and then it's also in the description of the later YouTube video. There we go. All right, so that's the idea of expanded form. Now, the other big thing in this chapter, in this section in particular, is there's nothing special about 10. So we use a base 10 number system. And our system has 3 criteria. You could kind of narrow it down to 2, is we group things by 10. Once we get a group of 10, we move on. So that's a big idea to think about. The other thing is we have 10 digits. 0 through 9. And then each place value is a power of 10. So we've looked at a couple of examples of that. So let's just write a few out. We have our ones place. Next to that, we have our tens place. We have our hundreds place. Next to that, and thousands, 10,000s, and so on. Ones, tens, hundreds, thousands, 10,000s, and again, each of these is a power of 10. 10's easy, it's the first power, the second power, the third power, the fourth power, and the 1 is the 0 power of 10. 10 to the power of 0 is 1. Right, so that's the way our number system works. When we write things down, the position of a digit, right? One of these digits up here is more than just the digit itself, right? It's that hidden meaning of place value. That takes a while for kids to learn that progression. But there's nothing special about 10. So if we think about money for a minute, and we just narrow ourselves down and only work with, say, pennies, nickels, and quarters, then we're making a base 5 system out of this. These are our place values here, these denominations of coin. Pennies are our ones place, nickels are our fives place, quarters are our 25s place, right? And I'm basing things on 5, literally 5 to the power 1, 5 to the power 2, 5 to the power 0. So instead of picking 10 as my base, I can pick 5 and kind of think about that historically. Why did we pick 10? There are lots of other examples in our lives where we didn't pick base 10. So the way we break up money is a mixed base. It's not really base 5, right? Because we have dimes in there, which doesn't quite fit this scheme. Dollars doesn't quite fit the scheme either. We have 20s, $50 bills. So we have some weirdness going on, and other countries with money do weird stuff too. But we'll come and look at some of those other ones in a minute. But let's play with just base 5 for a minute. I can write down numerals in base 5, and in base 5, I'm grouping by 5. instead of 10. I'm only going to have 5 digits. And think about this for a second. Of the 10 digits I have in base 10, 1, 0, a 10, that's made up of 2 different digits. There is no single digit for 10. And in a base 5 number system, that's going to be true also. The symbols are 0, 1, 2, 3, and 4. This symbol right here does not exist in a base 5 number system. There's no single symbol for 5, just like in our base 10 number system. There is no single symbol to represent 10. We have to use a place and another digit. And again, grouping by 5. So I'm going to break out a toy to help with this. And that toy is located in, let's see, it is, I think I can find it here. Let's go back to the Math Learning Center. Do they have a quick link back? They do not. I'll just do this. Okay, I want the money pieces one. This one's cute. So there's a couple of ways I can use this app. I can just play with coins where I have pennies that I put on the screen. So I would put a few pennies there. I can throw in some nickels. Throw in one more and a quarter. So that's one view of this. The other view is this grid view of it, which is kind of cute. So if I take 5 pennies, that fills up the 5 slots on the nickel. And a nickel is along here, and 5 nickels fill up 5 columns in the quarter. So that's another kind of fun way to view this app. I'm just going to use the normal change one for now. So let's suppose I'm playing a game, and every time I roll a dice, I get more pennies. And I roll the dice, and I get 2 more pennies. All of a sudden, I realize once I have those 2 more pennies, I can trade these pennies in for a nickel, which I'd always rather have a nickel than a penny. So I can select each of those, and I'm going to trade them in. So which button is that? This one maybe? Exchange for a nickel. There we go. Now, I couldn't make that exchange if I didn't have enough. So suppose I roll again and I get a 3. So here's the 3 pennies that I rolled the dice for. Right? And I might want to get a nickel out of that, but no one in fairness is going to do that for me because that's not enough for a nickel. And the app knows that too. If I try to do that, it's like, sorry, man, you can't exchange for anything. You just got pennies. Okay. And we're going to play a game where we try to get used to that idea of trading in, which is the kind of way addition works in our number system. So we'll come back to that in a minute. What do base 5 numbers look like? We got to have a way to distinguish them from base 10 numbers. And there's just a simple little trick they do in the book, and we do in other places. Because we have similar digits, right? Base 10 has a 0, 1, a 2, a 3, and a 4. So to tell somebody that I'm talking about base 5 and not base 10, if I write something down, then I put a little subscript word 5 right there. So once you see that right there, that means, oh, this is a base 5 number. It's not a base 10 number. So what does this number mean in base 5? Well, to know that, I have to identify the places. So like in base 10 and every other base, they have to have a ones place. And we usually put that on the right, but it doesn't have to be. The next place over is always whatever base you're talking about. So in our normal number system, it's a 10, but I'm in the base 5 world here, so that means this is 5s. And since we group by 5s, if I look back at that app for a minute, if I get 1, 2, 3, 4, 5 5s, let's do it. We have them there, right? They're dying to be a quarter. I can trade those in or a quarter. So though I could represent that as 5 nickels for sure, I think we'd all rather have a quarter than 5 nickels. So the next place value here, my point, is 5 fives, which is 25s. So what does the number 2, 3, 4 base 5 mean? It means I have 2 25s, and I have 3 5s, and I have 4 1s. Now, the cool thing about expanding a base 5 number or any other base besides base 10 into an expansion that looks like base 10 is now I know what this number is in base 10. If I have 2 25s in base 10, I would write that as 50. If I have 3 5s in base 10, I would write that as 15. And 4 1s is just 4. So 50 and 15 is 65 plus 4 is 69. If a number is written without a base written in a subscript to the right, that means you should assume it's base 10, but you could always write that there. So 69 in base 10 is the same amount of stuff as 2, 3, 4 in base 5. So let's just think about that with the coins for a minute. So let's clear this screen and start over. So I had the base 5 number 2, 3, 4. So that would mean 2 quarters, 3 nickels, and 4 pennies. It'd be easier to drag them than let them be randomly put on the screen. So this is the number 2, 3, 4 base 5 shown with quarters, nickels, and pennies. I could show it in the grid view. And I gotta rearrange things a little bit for that to look all right. Pennies are in the way. All right, so I can see all the stuff I have, and I can see there's 25 individual pieces here. There's 25 individual pieces there. So there's 50, 55, 60, 65, 67, 68, 69. So thinking in another base and comparing that to a base we are familiar with, that's not too bad. So once you learn the idea that base 5 means to group by 5, means you have 5 digits and your place values are based on powers of 5, right? Powers of 5 up there. Then anytime I write down a base 5 numeral, we should be able to easily convert it to base 10. So let's try a slightly harder one. Suppose I had 1, 3, 4, 2 in base 5. Now resist reading that as 1,342 because it ain't 1,342. So I have to identify what each place value means. So remember, the first place value here, that's always the ones. The next one is whatever base you're in. And then you keep grouping that by that base. So the next one would be 5 5s, that's 25. And the next one would be 5 25s, that would be 125s. All right, so these are powers of 5. So if I wanted to rewrite this as a base 10 numeral, I just have to identify the place values. So I have 1, 125. I have 3 25s. I have 4 5s, excuse me. And I have 2 1s. And then we just keep cleaning it up. What's 125? Well, that's just 125. So I'm just going to stack these now to add them up. 3 25s would be 75. 4 5s would be 20, and 2 1s is just 2. So what do we get? 5, 10, 11, 12. We get 3 and 7 is 10, 11, 12 again. So this must be 222 in base 10. So 1342 base 5 is 222 in base 10. These things mean the same thing. They count the same amount of stuff. They just do it in different ways. This one does it by groups of 10. And this red one up here does it by groups of 5. Groups of 5. Now, I don't think I can use the app to show that one. Let me see. Can't quite do it there, but I can kind of draw a picture of it on paper. So the 2, that's pretty easy. I'm just gonna draw 2 little squares. So there's my 2. That's really 4 5s, and 5s were those longer pieces made up of 5 1s, and I have 4 of those. The 3 here is in the 25 position, and that would be a 5 by 5 square. So that would look something like this. So I have 3 of those. Now the 125, imagine that these squares here have a little thickness to them. And if I stack them, I would get a cube. So I'm gonna say the 125 is a cube. That looks something like this. And it would measure 5 by 5 by 5. So inside there, 5 times 5 times 5 is 5 cubed. That's my 125. So again, think about my expanded form. I have 125 here. I have 3 of the 25s. I have 4 of the 5s, and I have 2 of the 1s. And all of that stuff can be regrouped in groups of 10. So in groups of 10, there'd still be 2 1s. They're going to be the same size. Right, so try to draw the same size as those. But a 10, right, it's going to be longer than a 5. It's going to be twice as long. So a 10 is going to look something like that. I have 2 of those, and then 2 hundreds. So like this is 5 by 5. Here I have 2 10 by 10s. So they're going to be a lot bigger. So my point here is the green stuff is the same amount of stuff as the red stuff. They're just different ways to express that much stuff. If we break this down into individual objects, there's the same amount in this red space as there is in this green space here. Just different ways of organizing, different ways of grouping that information. Base 5 versus base 10. Now, there's nothing special about 5 either. There are other number bases out there that we use other day, and I just want to name a few of those and then just use a couple. Common one we use is time, and time is really weird. We use seconds as kind of our smallest time unit, but really you can have tenths of a second and hundredths of a second and milliseconds. But we often think about second as a small unit of time. And then, so that's 1 unit. Let's say that's our smallest one. And then our next one up is minutes, right? In minutes, that's 60 seconds. And then we have hours, right? Hours, and hours are 60 minutes. Why 60? Think about seconds in an hour. That would be 60 times 60. There's 3,600 seconds in an hour. Why? And then we have hours in a day, 12 hours in a day. Why did we do that? So at first, when we play with our time, we have a group of 60 and another group of 60, but then all of a sudden we jump to a group of 12. So it's not as consistent as like our base 10 number system, but it is a different number system. This one starts off as a base 60 number system. Another example, when we measure stuff for cooking in this country, we have cups, we have pints, we have quarts, we have gallons, and this is just weird stuff here too, right? If we think of a cup as a basic 1 unit, then there's 1 pint is 2 cups. And then there are, let's see, 2 pints in a quart. I haven't thought about this in a while. And there are, in 1 gallon, 4 quarts. So this one kind of starts off as like a base 2 number system, but then we just make a jump to 4. Was there something in between at one time? I'm not sure. All right, so that's another kind of number system. And the more we dig around, we'll find other ones. I mean, think about inches and feet. That's another number system of its own. And these are kind of different societies, took other societies over in different times in history. And there's, if you look back in history, you'll see where some of these came from. Why they came about, that's a whole nother story. But cutting things in half, that's not too hard. That makes a lot of sense. The 60, that's a little harder to figure out why they picked 60, but there's a couple of theories about that. Now, the Mayans, thousands of years ago, had their own number system, and theirs was base 20. But they didn't have 20 digits. They only had 3 digits. Oops, digits. They had a digit for 0. It was this clamshell looking thing. That's my best clamshell there. And then they had a digit for 1. It was a pebble, a little dot. And then they had a digit for 5, which was a stick or a bar. So shell, oops, pebble, stick. So these are the digits. They only had 3 digits, and that's okay. You can get by with 3 digits. You don't have to have, even a base 10 number system, we don't have to have 10 digits. We could do things other ways. Think about Roman numerals, right? They don't really have a single digit for 2, it's 2 ones. So prior to the current number system, we did at least, where my ancestors were Western European mostly. Before they started writing things the way we do now, they wrote a lot of Roman numerals, which is not quite the same. Other thing about the Mayans number system is they wrote their 1s at the bottom. Above their 1s went their 20s. And then they made a jump to 360. So if it was a normal base 20 system, their jumps would have been multiples of 20. And so we would expect that to be a multiple of 20. So instead, that would be a 400. And then to keep going after that, times 20 would be 8,000. Okay, and there is some evidence that the Mayans did something like this sometimes, but usually what they did is on this stage right here, they multiplied by an 18 instead, and they stuck with that 3,600, that 360. But then they went with 20 after that. So instead of 8,000, if you take 20 times 3,600, you get 7,200. So Mayans did this jump right after the 1s. They jump by 20 first, and then they jump by 18 to get 360. And the 360 was important. Let me just clean this up a little. Because it's close to the number of days in a year. So they knew there were a little over 360 days in a year, and that there were 5 and around a quarter extra days besides the 360. And they kept track of those extra days, but when they counted, they just used 360 instead of the 365. So in a Mayan system, again, ones are at the bottom, next place is 20s, then we go a multiple of 18 to 360, and then 7,200 was above that. So what if I saw a number in Mayan? What would it look like? Mayan numbers, again, they're stacked vertically. So maybe I would see something like this, a stick and a couple of dots, and then maybe another stick or two. And then let's say I have another group there. So if I saw this and I wanted to identify what number it was, well, I see three groups. So I'm going to assume the bottom is my ones. The next group is definitely my 20s. And the next group is my 360s. How many 360s do I have? Well, I have 5 and 5 is 10. So if I want to translate this number into our number system, knowing what I know now about what these digits mean and how their place values run, I would say there are 10, right? 5 and 5, 360s. And there are 5, 10, 11, 20s, and then 5, 6, 7 ones. And so let's finish that. Let's see, 10 360s would be 3,600. 11 20s would be 220. And 7 ones is just 7. So we have 7, 20, 600, and 200 is 800. So this number written right here, I'll circle it, is the Mayan way to write 3,827. Right? So this 3,827 is a base 10 numeral versus the Mayan numeral over there. So throughout history, there's been different ways of writing down this idea of number, the things that we count. And it's only in recent history of humankind writing that we've settled in on this base 10 system.